Hi, I'm Michael Contario, and this is my submission to the Geek and Sundry vlog channel, The Fundamental Interconnectedness of All Things, which is both a reference to Douglas Adams, who was great, but also a description of what the vlog is actually about. Because I'm a physicist, and I love the universe, it's great, and the fact that we can understand it, mind-blowing. We've worked out that it seems to work with a couple of just fundamental physical laws, which also govern our brains and the fact the things that we're actually using to think about the entire universe. But I feel that a lot of the time people just go, oh yeah, physics, Large Hadron Collider, and pretty picture, Horsehead Nebula. And the fact that it's all about these laws gets a little bit lost. And so what I want to do is I want to look at lots of different situations, lots of different physical phenomena, and just explain how they're linked. You can go all over the place. You can look at things like people's smartphones, you can look at galaxies, the other side of the universe, or even, yeah, our own brains. And just start linking them together. And I'm going to start by linking the sodium street lamps, the ones that give you that sort of like weird yellowy glow, and how we look for planets in other solar systems. Now if you look at the street lights, the sodium ones, and they have that glow, and everything looks a little bit weird underneath them. You don't really see the colour, and that's because if you look at what we call the emission spectrum of the sodium street lamp, it's pretty much emitting at just one wavelength, one colour of light. It gives out like 90% of the energy that we put in as electricity comes out as light, and this wavelength is 589 nanometers, which is that yellowy colour. A nanometer is really, really tiny. It's a millionth of a millimetre. 100,000 nanometers is about the width of a human hair. But most of the things around it aren't that colour, so they just don't reflect that light. They don't give out that light, so they just look grey. But we can see, and the reason that we picked that light is because actually 589 nanometers is a colour of light that our eyes are actually pretty good at detecting, and so it was cheapest. Well, the reason that these lights only give off one particular colour is because there's a gap of energy where this is where all the electrons normally sit inside the sodium atoms, and then this is the energy that they can be at, and all the gap in between, they can't be at that energy. They can only jump up to that energy when we give them electrical energy, and then they fall back down and give out the one particular colour of light. If you look at something like the sun's really hot, and things that are hot give off a whole range of different colours of light, different wavelengths, like we do. But we're a lot colder than the sun, so we don't give out visible light. We just give out light which is actually in the infrared, and that's why heat-sensitive cameras pick us up. But with the sun, you've got this entire set of wavelengths, but there are some gaps in it. Just these lines where we don't actually see as much of that colour of light. And this is called the absorption spectrum. And the reason this happens is because there's some gas around the sun and kind of on the edge of the sun, and when the light goes into that, this gap, which is different for every different element, doesn't just tell you what light that element can emit, it also tells you what light can actually be absorbed by that element. So all the other colours just go straight through this gas, but the particular ones corresponding to that element get picked out and they get absorbed, and then they get emitted again in all different directions. They don't come straight to us, and so we don't see that. And so we can actually use the absorption spectrum to find out what gases are in between us and the source of light. The way we discover planets in other solar systems, all we're looking for is the dimming that happens when the planet goes in front of the star. And we can actually work out what wavelengths of light are getting dim when its atmosphere is passing in front of the star as well. And so this is what we're using to work out what elements there are in these atmospheres, and hopefully at some point we'll be able to discover planets which have an atmosphere like our own. And so therefore we might be able to say those planets might have life similar to what we have on Earth, which I think is pretty good going from starting from a street lamp. So join me next time, and I'll be talking about something else that we can discover from the light that we're getting from distant stars and in fact distant galaxies.